So the principles of building envelope design, when doing design, again, you must always consider these three basic forces of heat, air, and moisture. They are always interacting together. When thinking about moisture, we have the basic properties, the principles of moisture. We'll look at moisture movement, relative humidity, again, always worth reviewing because it trips us up constantly when doing our calculations. We'll look at the climates, we'll look at forms of water, we'll look at dew point as it relates to relative humidity, and then air pressures and heat flows. Now, moisture movement in general, we did our training earlier this year, we talked about the forms of moisture. In general, moisture is going to move four ways: gravity, airflow, capillary suction, or diffusion. That's going to redistribute the water. A lot of what confuses people in making predictions about moisture movement, though, is the form of water vapor. Water vapor and the misused concept of relative humidity that we get in the news every night explaining what the weather is going to be tomorrow totally trips us up, because the world is reacting simultaneously to relative humidity and absolute humidity. And they're two different things, and materials behave differently around them. So we're going to talk a lot about this again, which is why we're reviewing things like dew point and RH. RH is an expression of how much, relative to the temperature, how much water air can hold. If you take a mass of air and increase the temperature, the humidity goes down. If you take that same mass of air, volume of air, and decrease the temperature, the humidity goes up. As the air cools, it can hold less. Now this becomes very, very important towards moisture management, because water vapor drive, the movement of water vapor through your building assembly, is a reaction to the difference in pressures across the assembly from high pressure to low pressure. Nature always goes from high to low, and the resistance of the layers in between will control the rate at which that vapor flows through. Now, that's a very straightforward way to calculate the rate at which the moisture moves. But what happens to the moisture on that trip is really the hard part, because of the fact that we have materials with capillaries. If you remember, we talked a lot about capillaries in the moisture management training. Capillaries are those materials or those natural tubes that occur within materials that are grown or manufactured not under heat and pressure. Now, if you remember this high school chemistry moment, the air pressure outside, that causes the dew point to be much higher. This means that at 65% relative humidity outside of that assembly, somewhere inside that assembly, 100% relative humidity could be occurring. Condensation can be occurring within materials when it does not occur on their surface. And this is why wood has a naturally occurring wood moisture content, which for, say, here in Philadelphia ranges between 8% in the early spring up to about 13% in the fall. It's constantly changing up and down based upon humidity outside and the fact that these capillaries are condensing moisture out of the air. This occurs in all our buildings. So when we watch this humidity migrating through our assemblies, we have to avoid getting humidities above 65% or especially 80% whenever around materials that have capillaries, or else what was water vapor being driven through the wall will actually start to condense back within the materials. When you have a material that goes above 17% wood moisture content, if there is food present, it will grow mold. So this is why we get to talking about designing for mold resistance. When we're designing for mold resistance, we're designing for low humidities. We have to keep the humidities interstitial to the envelope below 65% RH, ideally always below 80%. We never go above 80% relative humidity for 30 running days when temperatures above 41 degrees Fahrenheit or below 104 at any layer of the envelope, or else we have mold growth potentials. That's that ASHRAE standard 160 you've heard me talk about before, design criteria for moisture control in buildings. This is the new yard mark. We used to do dew point calculations where we'd figure out if condensation would occur. We already know that if condensation occurs for 1 day, it's way too late. We're already in mold growth potential. Now what we try to avoid is 80% relative humidity for 30 running days when temperatures above 41, below 104. And that's our guideline for how we're going to deal with humidity. Now we know what humidity we can live with, less than 80. This becomes really important in terms of moisture drives. We start talking about the climates. We used to have that climate zone map that had the 17 different climate zones in the United States. Now we've got the 7 climate zones divided up between east of the Rockies being humid year-round, west of the Rockies being dry, and zone 4C marine up in the Pacific Northwest, which is extremely wet. Now this becomes important when talking about water vapor, because essentially if you're east of the Rocky Mountains and water gets inside your wall, it's not going to drive to the outside. It doesn't move that way. The vapor pressure outside is too high year-round. You have very high humidities, very high temperatures, creating very high pressures. Now you've got a layer inside your wall, say your OSB sheathing becomes wet. For vapor to move to the outside, it's got to be a lower pressure outside. The chances are, though, if the sun is beating on this house, the surface temperature is going to be 120 degrees Fahrenheit, causing a film of relative humidity at that point to increase the amount of moisture it holds. You all of a sudden get a very high vapor field around your house. The moisture cannot move to the outside. You're not going to dry to the outside when you're east of the Rockies. West of the Rockies, disregarding Zone 4C Marine, man, you can dry to the outside all day long. You can have a house made out of EIFS, and you know woodpeckers love EIFS, and they'll go up and they'll knock their head on it. It sounds like a rotten log, so they'll chunk out a big piece the size of a grapefruit. That can be left open in Denver, Colorado for 20 years. And you can check your probe and poke it into that OSB sheathing, and the sheathing is bone dry. You do that in North Carolina, in 6 months, I guarantee you are tearing that thing down because of all the moisture in the air when you're east of the Rockies. So the climate is very important towards vapor drives. You must be aware that when you're east of the Rockies, you're never going to drive to the outside. That means you're going to drive to the inside, which is why the building code has changed the requirements for vapor retarders. If you look at 2009 building codes, they used to have the vapor retarder as 1 US perm or less. Now we're talking about 3 types, below 1, 1 to 10, or 10 or above, depending upon where you're at in this country. Because if you're east of the Rockies, you actually don't want a very big, very strong vapor retarder, a very low permeance. Something like polyethylene or visqueen in this part of the country, a traditional choice of material to use, actually gives you 0 potential to dry to the inside. If your window leaks, you're never going to drive that moisture through that film of polyethylene. So the code has said, hey, open up a little bit. Give yourself a little more breathability so that you can dry to the inside and help get some of that moisture out of the wall, because again, the moisture is always going to get in. We're never going to keep it out. In general, the rule of thumb is that moisture moves from the inside out in the winter, from the outside in the summer. It's basically going from high pressure to low pressure. For most of us, the high pressure in the winter is on the inside. So, if we look at the air temperature outside and the ambient conditions of our climate, it looks like the vapor should drive from inside to out. That's just the rule of thumb. And beware, rules of thumb aren't always correct. The fact is that it's much more dynamic than that, because the vapor doesn't see the air on the outside. The vapor on the inside of the house actually can't really see beyond the outside surface. So what we wind up with is, say if we're in a northern climate, we wind up with a very warm wall in the sun with vapor driving in, even though it's the middle of winter. And as soon as the sun goes down, it flips and come out. Now in the south, typically because we have a very warm temperature and high humidity outside, it's almost always driving to the inside when we have air conditioning running. So we have an outside-in drive. But something to be aware of is that, just like this energy flow, why do we only require R11 walls in Florida? Because the delta T across the wall is only 20 degrees Fahrenheit. If energy flows in relationship to the difference in temperature and resistance of the layers in between, just like vapor does, the difference in Florida is actually very small because the temperatures are so close. Whereas if you go to a place like, say, upper Midwest, the temperature from inside to outside can be extreme. It can be as much as 80 degrees difference. So you have a much bigger temperature drive, and consequently you get a much bigger vapor drive too. So the vapor drive from the south, from the outside in, isn't nearly as strong as the wintertime from the inside out in the north. We typically see a lot more mold problems in the south though, because mold only lives or only goes aerosol. When people have a reaction to mold, it's most closely described as an allergic reaction. That is not medically true. It is not medically a allergic reaction, but for most of us, that's the easiest way to think about it. You're going to react when those mold goes aerosol, when it starts putting its spores out into the air, which is when it's above 17% moisture content, when temperatures between 41 and 104, that's when it does that. That's when you react. You don't want to react to it, make it too cold, right? So in the north, we don't have typical mold problems in the winter, even though we have these really big delta T's, because the temperature where the moisture is occurring is cold. The moisture typically occurs in the outer parts of our building envelope in the north, in the winter, temperatures below 41, we have no mold growth. In the south, no matter what you do, you're going to be between 41 and 104. You always got the perfect temperature for mold growth. So any moisture issues down there, you're doomed. It's going to grow. You've got to dry that stuff out in a hurry. In the north, you've got about 4 or 5 months where you don't care, because you've got the water buildup on the cold layers at the right time of year. As long as you can move that moisture out again before it goes above 41 for 30 days, you're going to be okay. That's why the code has opened up those definitions on vapor barriers. So letting you be more breathable up there now, because they're going to let you get a little bit wet in the winter. They don't care. It's too cold. As long as you can dry it back out again when it gets warm. How do you dry it out again? By being open to the inside. So that's why the code has made these changes. With our climates, again, it's always important not just to think about the interior and exterior air temperatures. It's very important to think about the surface temperatures of the walls. A red brick wall behaves completely differently than a white vinyl wall does. The red brick wall in the north gets very, very warm. But it's very important to properly position air barriers to prevent air infiltration in and out. Now, air barriers, we see them required by the 2009 building code. Residential and commercial codes have them. They're typically installed at the point of the water-resistant barrier, which would be on top of the sheathing. When you're going to choose that location to put it, you have to now stop and think. You've got a science problem on your hands. Should my air barrier be vapor open or vapor closed? Do I want to breathe vapor through it easily or have some resistance? It is a very difficult question to answer, and one that we typically use computer models for. If we're going to have a rule of thumb that we're going to use, there's two in this case we've got to depend on. The first one is one of the oldest ones we have in construction. Never create double vapor barriers. Never have two, because if water gets in between, and it's not getting out. So we don't do that. So we know already we don't want to be below 1 US perm on that outside layer, which means peel and stick membranes are very dangerous. One of our traditional uses for an exterior water barrier and air barrier was the peel and stick membrane. If you do that, your interior vapor control's got to be really unique and really tricky. Because you can't have a standard vapor retarder on the inside, or else you've got this double barrier. Again, if water gets in from a leaky window, you're doomed. So how do you prevent that moisture drive in the winter from getting to the backside of that rubber without causing you drying problems? There is a solution, and I can't give it to you now because it is a proprietary solution, but there is a solution, there is a way to do it. In general, though, what we try to choose out there now is we see vapor permeable air barriers. Air barriers around 5 to 10 US perms. Fluid-applied, trowel-applied membranes that conform to the surface and are somewhat breathable. For most of the US, with most types of construction, 5 to 10 US perms, water vapor permeance for the air barrier, is a really workable number. It works very well in general. There are specific instances that might want one higher or lower, but in general, that's a pretty good rule of thumb. Water can typically exist in four forms: solid, liquid, vapor, or absorbed. You can deal with water as a solid. As a liquid is pretty easy. As vapor we talked about, absorbed is a whole different thing. Absorbed actually implies that you've got water now being absorbed into the cellular structure of a material. When materials start absorbing moisture from the air, we talked about a capillary in a piece of wood, that tube that grows inside that piece of wood with lower air pressure, so the higher dew point, so you start getting condensation. Once that capillary fills with water, you actually go to cellular absorption. It goes inside the cells of the wood. Once that water gets in there, you are not getting it out fast enough to stop you from having a problem. Once you've got capillary saturation, you're in big trouble. To dry that lumber out, you typically have to go into an oven to dry it fast enough, and that's not going to happen. So we really want to prevent absorbed water from ever occurring. We talk about moisture and dew point. I talked about the dew point before. This is actually a screenshot of what's called a psychrometric table. Psychrometric tables and charts are the relationship of relative humidity, how much moisture the air can hold at a given temperature. This actually shows you in inches of mercury the absolute vapor pressure at different temperatures. If we talk about the vapor pressure at 20 degrees Fahrenheit, it's 0.1. If we talk about it at 80 degrees Fahrenheit, it's actually 1. It's a 10-fold difference in pressure. As the air goes up, the pressure in the air goes up very, very rapidly, which is why we have a lot of problems and a lot of issues with this whole dew point concept. That these are very, very strong forces up here, less strong here. We've always been worried about these wintertime vapor pressures. This is where we're getting killed by now. It's summertime. It's high temperature pressures. A lot of pressure to move a lot of water. There is a movement out there now. People talk about moving the dew point outside the wall. You have the Boston masonry wall, right? Very common out of Boston. We're seeing it up in upper Midwest now, places like Chicago, where they're getting rid of all the cavity insulation from inside the framing. And they're taking 3 inches of extruded polystyrene and they're sticking out in that brick cavity. So you got the brick, you got the air spaces, you got 3 inches of extruded polystyrene board, then you got your gypsum sheathing, you got your, then you got your stud space and your drywall. No insulation between the studs. Now the reason they do this is to get all that insulation value out in the cold, wet part of the building. When you do that, because the extruded polystyrene is a vapor barrier, the inside and the outside both work for you. In the wintertime, water vapor can't drive from the warm interior environment out into the cold insulation because it can't get past the interior face of the insulation. It's a vapor barrier. So you don't get that moisture buildup out in that foam. In the summertime, when that red brick wall is storing tons of moisture and the sun comes out, the air conditioning can't pull it into the building because it can't pull it through that foam board. It's a very successful model. People refer to that as moving the dew point out beyond the sheathing. That is not technically true. When you do this and you do this right, there is no dew point. Relative humidity of 100% is never realized. So anybody who says they want to move the dew point to the outside of a building, I say they should go back to their calculations and look a little bit more, do a little more work and prevent the dew point from occurring. We don't ever want the dew point to occur no matter where. That's our goal with our designs. And it can be very easily done. You just need to think about it and run your simulations and do your calculations. Now air pressure, we always talk about air and heat when we talk about moisture. Why? Well, because air moves a lot of moisture, right? That's carrying a lot of moisture with it. When that air comes up against a cold surface, that air film on that surface is going to give up the spore. You're going to get condensation. You're going to get the side of a glass of iced tea in the summertime. So we worry about these airflows, and they're constantly changing within our buildings based upon interior pressures, exterior pressures. We talked about the biggest fan winds. Biggest fan in your house is your dryer, 300 cubic feet per minute of air. It's exhausting from the house. When the wind blows across the house or a building, you get a positive pressure and a negative pressure. Positive pressure forces air in, negative pressure sucks air out. So you've got this constantly changing dynamic of air movement through our buildings. This is what air barriers are supposed to help us with. They're supposed to give us a consistent layer of control, a seamless integrated layer within our building to prevent air from passing through so we don't experience these pressure differences of moving a lot of moisture and moving a lot of energy. Now the heat flow, because heat, air, and moisture are always together, heat flow, like that water vapor, is reaction to pressure. The bigger the temperature difference across it, the more energy is going to flow through. There's the old rule of thumb that says moisture moves with heat. So if you want to imagine which way the moisture is moving through your envelope, picture which way the heat is flowing from hot to cold. Now that is a coincidence. That is not a cause and effect. But it's a coincidence that generally is held true in most cases. If you think about what is hot and what's cold, that's the direction moisture is moving to. It's also moving towards the cold.